We're going to tackle one of the oldest, deepest questions in all of science. What exactly is light?
For centuries, this one simple question completely divided the greatest minds in physics. They were literally battling over the fundamental nature of light itself, and that debate, it would end up reshaping our entire understanding of the universe.
So, on one side, you had this idea of light as a particle, like a stream of tiny little bullets firing out from a source. And on the other side, you had the idea of light as a wave, kind of like the ripples you see in a pond. This single question kicked off one of the longest and honestly most fascinating debates in the entire history of science.
Okay, let's dive into round one. In this corner, weighing in as the undisputed heavyweight champion of 17th century science was Sir Isaac Newton.
Now, when Newton talked, everybody listened, and he proposed that light wasn't a wave at all. Nope, he was convinced it was a stream of tiny, superfast particles all traveling in a perfectly straight line.
He even gave them a name, corpuscles. And what's so amazing is that his theory was incredibly successful. It just seemed to explain so much about how light works in the real world.
For instance, reflection, super simple. The little light particles, his corpuscles, they just bounce off a mirror like a tennis ball bouncing off a wall. It made perfect intuitive sense to people.
Newton didn't stop there. He also tackled refraction, the way light seems to bend when it goes into water. His idea was that some kind of special force at the water's surface was actually pulling on the corpuscles, changing their path. It was another simple mechanical explanation that just seemed to fit perfectly. And what about color? Well, he argued that different colors were just particles of different sizes. Red corpuscles were the biggest, violet were the smallest, and a prism, that was basically just a machine for sorting them out by size. It was this neat, powerful, and totally mechanical explanation for everything.
So, for more than 100 years, Newton's particle theory was king. But cracks were starting to show. A challenger was stepping into the ring with some evidence that you just couldn't ignore.
See, scientists started noticing something that particles, they just shouldn't be able to do. They saw that light doesn't always travel in a dead straight line. It can actually bend around corners. We call this phenomenon diffraction.
But the real knockout punch for the simple particle theory was the famous double-slit experiment. So when you shine a light through two tiny little slits, it didn't just make two bright spots on the screen behind them, like you'd expect with particles. No, it did something really, really weird.
Instead of two spots, it created this whole pattern of bright and dark stripes. And here's the crucial thing. That interference pattern, that's a classic signature of a wave. And so it happens when waves add up in some places and cancel each other out in others. There was just no way to explain this with tiny, solid bullets.
The conclusion was just inescapable. As more and more evidence piled up, it became obvious. Light couldn't just be a particle. It absolutely had to be a wave.
So, the wave theory wins. Victory! But right as physicists were taking their victory lap, a brand new experiment uncovered a shocking puzzle that waves just couldn't solve. It was called the photoelectric effect.
Okay, so here was the problem. According to wave theory, any color of light should be able to knock electrons off a piece of metal. You just have to make it bright enough, right? The energy would just build up over time like a wave hitting the beach and eventually pop an electron loose.
But that is not what happened. For instance, if you used red light, which has a low frequency, nothing happened. You could crank up the brightness, make it blindingly intense, and not a single electron would move. Nothing.
The wave theory also predicted something else. It said that if you make the light brighter, if you increase its intensity, the electrons that get knocked off should have more energy. They should fly off faster.
And yep, you guessed it, the experiments disagreed again. Making the light brighter didn't change the energy of the electrons one bit, it just knocked more of them off. The wave theory, the very same theory that had just dethroned Newton, was suddenly completely broken.
So the whole debate was thrown wide open all over again. Was light a particle? Was it a wave? Was it something totally different? The chaos reigned until a young patent clerk named Albert Einstein came along with this revolutionary idea that somehow managed to honor both sides of the fight. What Einstein suggested was, hey, what if we stop thinking about light as a continuous wave? What if it's actually made of individual, separate little packets of energy? And he called these packets photons. And this simple shift in thinking, it solved everything. All of a sudden, the photoelectric effect made perfect sense. It's a one-on-one deal.
One photon hits one electron. A photon's energy depends only on its frequency, its color. So if that low-frequency red photon doesn't have enough juice to begin with, sending billions of them isn't going to help. And brighter light, that just means you're sending more photons, so you knock off more electrons, but no single electron gets any more energy. It's beautiful.
So, after hundreds of years of debate, the mind-bending conclusion we arrive at is that light isn't an either-or kind of thing. It has a dual identity. It behaves like a wave when it's just traveling through space, that's how you get those interference patterns, but it acts like a particle the moment it hits something and interacts with matter.
This strange duality is the bedrock of quantum mechanics, and it leaves us with one last profound question that physicists are still grappling with today. A question that challenges our very idea of reality. If light only picks a side when we look at it, what in the world is it when we're not looking?